This is section 2 of the lecture for chapter 1, section 3 in the book Problem Solving with Differential and Integral Calculus. Here we're going to be looking at the slope of a line that is curved. So the slope of the line is the rise over the run. The rise is the change in area. And the run is the change in the side length. So for those 2 points, we can put them in. Delta A is 39 square centimeters. Delta S is 3 centimeters, the change in the side length, or the difference in the side length. The problem is the slope's different. It's a lot steeper at 8 centimeters than it is at 5 centimeters. If we get the slope by just mindlessly dividing 39 square centimeters by 3 centimeters, that's neither the slope at 5 centimeters or at 8 centimeters. So how do we get the slope at a point? What does it even mean? What's the rise at a point? Is there a rise? Is there a run if you're at a point? So what we do is we get the slope by drawing the tangent line at the point. One thing we can do, if we don't know differential calculus, we can draw a tangent line. So that approximates the slope at the point, like that. So the slope at 5 centimeters is the same as the slope of the tangent line at 5 centimeters. So instead of getting the slope by using 2 points on the line, we get the slope of the tangent line at the point. So the rise of the tangent line goes from 0 to 75 square centimeters. The run looks like it goes from about 2.5 to 10, which is 7.5 centimeters. So the slope is the rise, 75 square centimeters divided by 7.5 centimeters, which is 10 centimeters. And that slope is different from the slope at 8 centimeters. At 8 centimeters, it's a lot steeper. Let's draw a tangent line at 8 centimeters, and you can see that's a different slope. The rise here is 96 centimeters, 0 to 96, and the run goes from 4 to 10, which is 6 centimeters. Slope is the rise over the run. 96 square centimeters divided by 6 centimeters is 16 centimeters. And just for completeness, we can calculate the slope at 2 centimeters. The side length of 2 centimeters, draw a tangent line there. The rise looks like 36 square centimeters, and the run is 9. It goes from 1 to 10. So the run is 9, the slope is 4 centimeters at the side length of 2 centimeters. Wherever we want the slope, we have to draw a tangent line and get the rise over the run of the tangent line. Now we're going to look at the contributions to delta A. 2s delta s and s squared. Those two contribute to the delta A. So here we are. Our familiar side lengths, 5 and 8, give us the areas of 25 square centimeters and 64 square centimeters respectively. The difference in the side length is 3 centimeters. The difference in the area is 39 square centimeters. The linear part of delta A is 2s delta s. That's responsible for the straight line. The nonlinear part, s squared, is responsible for the deviation from the straight line. So this part is the linear part. The linear part in this case is 30 square centimeters. The nonlinear part is 9 square centimeters, and the nonlinear part is right here. And I'll show you that. That's the linear part. That's 2s delta s. That's 30 square centimeters. There's the nonlinear part. That is 9 square centimeters. And you can see that if I go smaller, the change in delta s is smaller. The relative contribution from delta s squared gets smaller and smaller and smaller. And pretty soon, almost all of the contribution is from the linear part, which is 2s delta s. In other words, if we zoom in to any curved line, it's going to look straighter and straighter and straighter the more that we zoom in. So let's do that. Let's zoom in. Instead of going from 0 to 10, I'm going to plot from 4.8 to 5.2. And we're going to go from 23 to 27. This little square right here is going to be the entire plot. Here we go. There it is. There's our anchor point. 5 centimeter side length, 25 square centimeter area. And this line looks pretty straight. You can see that there's some deviation at the ends. Deviates a little bit. You can see the tangent line. That's the straight line. The dark line is the curved line. Now, instead of going from 5 to 8, 8's not even on this graph. Let's go from 5 to 5.1. So our delta S, difference in side length, is 0.1. And we can calculate the change in the area. We got 26.01 and 25. That's 1.01. The contribution here is almost all from the linear term. You can't even see the nonlinear term contribution. And we can do some math. There's the linear contribution, 2S delta S. That's 1 square centimeter. And delta S, which is 0.1, we square that and we get 0.01 square centimeters. So the total delta A is 1 square centimeter plus 0.01 square centimeters. Almost all from the linear. And you can imagine that if we go zoom in even more, the nonlinear contribution is going to get really small. So who cares about the contributions? Well, the smaller the relative side length change, the smaller the nonlinear contribution, and we can ignore it. We can throw it out completely when it gets really small. And you'll see more of that in chapter 2. So now, takeaways from section 3 of chapter 1. The relationship between the area of a square and its side length is nonlinear. The line is curved. It's different. The difference equation for the area of a square can be derived from the normal equation, which we did. I'm not going to put the equation here because the equation isn't the important thing. It's the concept that it's important. The relative contribution from the nonlinear part, delta S squared, becomes small when the relative change in side length is relatively small. And we dealt with the slope here. The slope of a curved line at a point can be determined by drawing a line that's tangent and getting the slope of the tangent line. So to test your mastery of these concepts, there's exercises and problems in the textbook at the end of this section. And now, since this is the last section in chapter 1, we'll do a takeaway of chapter 1. We introduced difference equations. Here they are. We have the perimeter of a square, the circumference of a circle, the area of a square. The normal equations are the ones you're familiar with. The difference equations give the difference, the relationship, the difference. If I change one, how does the other respond? Now there's 10 practice exams at the end of the chapter. They're challenging. Get stuck and struggle and grind. And then when you're done, you can watch a video. We have video walkthroughs of every problem on all 10 exams available at edmeyer.phd. Get to work.